This is a lecture especially tailored to graduate students, and so I apologize to the professors being present to use their time very kindly, but it's meant to be for you, so please ask questions or interrupt freely if you don't understand what I'm showing you. Okay, don't be afraid. Right, so I will try to give you in 1 hour more or less the state of the art of what has been doing and has been working in terms of topological approach to fluid mechanics. And I cannot cover everything in 1 hour, so I start from scratch, from a little bit of history, and then I go through some proofs of results, and then I land with the last 20 years of work with a couple of information, okay? So this is the plan. Right, so let me give you a summary, a brief entry to what we call topological fluid mechanics. Then I will give you again a very short idea of discussion on frozen fields in ideal diffeomorphisms of flow maps. Then I will focus on conservation of these quantities, magnetic and kinetic helicity. These are conserved quantities of ideal fluid mechanics, and they are playing an important part in this context. Then I will show you relationship between these quantity helicity and topology in terms of linking numbers. I will also mention topological changes due to dissipation and viscosity, so no longer ideal processes, but real processes. And then finally, just mentioning what has been done in the last, say, more or less 20 years of work, energy and complexity, finding relationship between these two in particular here, vortex tangle. So this is the program of today. And let me start with a little bit of history, and this is actually well known, but these sketches are my own copies from Cambridge University Library of the original private notes of Kelvin. So these notes you don't find in books, and are, of course, I have been allowed to show them. And you see here is the idea of a vortex atom theory. Maybe you know it. I just mentioned the fact that in the idea of Kelvin is a modern idea, current idea of Ed Witten's and others in high energy physics. What is the idea? The idea is to have a model for particles, microscopic particles. And his ideas for particles was, okay, let's think of a vortex ring like in water, but in ideal fluid, ether. So it's a hypothesized existence of ideal fluid, and this vortex ring is imagined to be very, very small, microscopic. Now you think of a vortex ring, you think of another vortex ring linking with the first, and then you get the two rings together, and the topology of different states quantize the energy of different states. So in Kelvin's idea, use of topology meant to be a way to quantize energy. And quantization of energy was already known at the time of Kelvin from spectral analysis of chemical elements. So this is the idea. Why vortices in ideal fluid? Because these were proven mathematically to be permanent in time, their existence. That was done by Helmholtz. Here are some sketches. We are more or less 1878, and you see here is a sketch of a possible trefoil-shaped vortex Here is a representation of a braid. No work was done on braids, and so he had this very interesting idea, and possibly a combination of a braided pattern over a complex knot. So it's quite remarkable. Of course, he couldn't do this in terms of search for topology. Topology didn't exist. The word was introduced by Listing almost the same years. So he asked a collaborator, a younger collaborator, Tate, to classify topological states, knots and links. And this was done by Tate, more or less same time he started to classify works and then to classify knots and links. This is the first table that he produced, and you see 7 years later. And this table analyzed the first differences between topology in a number of situations. And remarkably, this went on and on. He discovered many, many things, and then he kept going for several years, sometimes being depressed by the lack of progress, sometimes being excited by the lack of progress. And after other 10 years of tabulation, we have this amazing table of knots and links. This is done by hand, by pen and paper, and by playing with ropes on the ground and trying to identify the differences, the topological differences between one, say, this system and that system and so on and so forth. No mistakes were done. Only one two-knot pair of knots were reproduced, and that was found only in 1970. 100 years later, Perko, a Japanese mathematician, discovered that there is a duplication of all these tables. So it's amazing piece of work he did. What happened since this original attempt? Now I jump to modern time, more or less. Well, Maxwell was immediately interested in this, and he wrote to Tate, and they stayed in contact for many, many years. So he was behind Tate tabulations for a number of years. And indeed, in Maxwell's book, you find already quite interesting things. First of all, there is a chapter called, I don't remember now, maybe preface or something like this. So it's the chapter before the standard chapters. So people skip pages. They don't read prefaces or something like that. You should read it, because he's totally dedicated, devoted to topology, to the fundamentals of topology. Quite amazing. And then you go to the second book, volume 2, and at a certain point you find a demonstration of Gauss linking number formula. Because the Gauss linking number formula of 1833 remained without proof. Gauss stated something, and then we had no proof. And the proof was given by Maxwell in the book on electricity and magnetism. And then, of course, the work of Kelvin. Today, after 150 years, we have many, many fields from mathematics to physics dedicated to this approach. Well, I'll stick to classical physics. Of course, there is also topological quantum field theory that matters. And in mathematics, one open problem is to find rigorous knotted solutions to Euler equations. And this diversifies in many, many different fields. The study of 3D fluid topology, vortex solutions, as I said, the role of invariance related to topology, and the aspects of stability. Very, very difficult and open. Another context is instead of vortices, if you think of magnetic fields or current fields, well, the question of energy and the relaxation to ground states. And here we have works on magnetic knots, electrically charged knots, and the relationship with the ground state of these knots and links. And then work again in mathematics on dynamical systems, existence theorems, and vector field topology orbits, structures, Hamiltonian structures related to invariance in fluid and in topology. And then one of the last but very important work is on the change of topology, because real systems do not have a frozen topology. They change a topology because there are resistive effects, dissipative effects, all sorts of effects. And the one key question here is to understand the role of reconnection in vortex dynamics or magnetic fields. And of course, there is a very important problem in mathematics associated with the finite time existence of singularities in, say, Navier-Stokes equation or Euler equation. So this is just a quick review. This is just a slide on some of the work. This is high energy, kind of high energy physics on Skyrmions, change of topology due to the reorganization of localized energy. Then we have, of course, work on complex systems, all sorts of complex systems, not only fluid systems, but imagine macromolecules, molecular structures in a box or in a cell. And then, of course, we have the study of magnetic fields, either in confined systems like tokamaks or in nature. And this is just a picture of taken from satellite observations of gigantic formation of magnetic, we should call them plasma loops. Plasma loops, and you see here, this is the surface, whatever it means, the surface of the sun, and this is just these structures. These structures evolve, are gigantic, they reconnect, they release energy, and this is the 90% of the energy we get from the sun comes from interaction of plasma loops. And of course, these are continuous evolution. If you look at these structures at the telescope, you see these structures moving, and there are very beautiful movies available on the internet, just to give you an idea. This is one of the key interests in this sense, in astrophysical flows. Now, an entry, mathematical entry to what we are going to see is very sketchy. So consider, for example, the case of magnetic fields. And then I go back to vortex filaments. Well, in ideal MHD, we have no viscosity, no dissipation, no resistivity. We take it as incompressible and perfectly conducting fluid. And this is the velocity of the fluid. This is the vector position of particles. And this is time. Because it's incompressible, I put here the condition divergence less for u, and eventually u going to 0 at infinity. So imagine that you have a fluid where magnetic fields are there, and what you have is the key equation, the governing equation is this, and you should recognize this equation is a very well-known equation under the name of Faraday. This is Faraday's equation. The change in time of the magnetic field in ideal condition provides this evolution. The curl of U cross B, assuming that we have no monopoles, divergence less for the magnetic field and finite energy. So this is the governing equation. And under this equation, in ideal condition, what we get? Well, we have the structures. Imagine localized structures, magnetic field in a tubular structure, in a tubular geometry. So we take at an initial time a mapping that produces the evolution of this tube. We put a magnetic field in this system, and this you may recognize this as the Cauchy equation to this equation. Cauchy equations. We go back in time, at the time of Cauchy, and we establish a correspondence between initial field at time t equals 0 and the time t of the evolution, and the correspondence is established through this deformation tensor that controls the deformation, the volume change in volume, the deformation in under stretching, under continuous deformation of the initial volume. Under continuous deformation, whatever complexity you have for the magnetic field, that is transferred at the initial time t0 to time t. So we establish a topological equivalence between something initially given and something that we get afterwards. Remember, this is ideal. Of course, when we have dissipation, etc., topology breaks all these ideal scenarios. What does it mean this in practice? Well, in practice here, I give you a simple example. It's almost a toy example. Imagine that this is not a magnetic field. Imagine that this is plasticine, something deformable that you can play. So it's kind of solid something. And you deform it to this, and after continuous deformation without cuts, you transform this into that. Can you imagine how to do this deformation without cuts? Well, this is a typical exercise for everybody, and when I was young and I met this example, I struggled without the solution. I struggled to find the solution. It defies intuition. But the solution is this. First, you take this and you deform this part into this. And then what you do is you twist up this part here, the bridge, and then you enlarge this part. And then when you're there, it's done. Because you take this part and you remove it on the other side. So you get that. So it's a kind of twist, stretch, and fold mechanism. I will talk about this twist, fold, and stretch mechanism in my seminar tomorrow. So the lecture of tomorrow will be devoted to this particular combination of three moves that conserve topology. So you will see in nature and in mathematical physics how these go. Now, the title was on the conservation of helicity. I mentioned the fact that helicity is a new conserved quantity of ideal fluid mechanics, so I will give you a proof of this. I mentioned magnetic fields and I mentioned vortex dynamics, so I will give you a proof that these quantities in the context of magnetic field and in the context of vortex dynamics are conserved. So this is the first step. Is a kind of standard knowledge now, but it's not in books. Okay, it started to appear in books, but it's not in the classical books of fluid mechanics. Amazing, because we have conserved quantities like kinetic energy, linear and angular momenta for fluid systems, but helicity has been discovered to be conserved only maybe 80 years ago. So it's a pretty recent discovery. So this is the definition of magnetic helicity. You see the integral of A dot B, B being the magnetic field in a volume, say, of Vm, and then A is the vector potential. And then we request that at the boundary of this volume, actually I assume to be infinitely open domain, but if we have a boundary, we require that the magnetic field does not go through the boundary.
You mean it is conserved, so it must correspond some symmetry.
Yes, it does.
Symmetry and
Of course. What I'm going to show you is the proof of conservation not based on Noether theorem, but yes, you can obtain the same proof, conservation of helicity under Noether theorem, and it corresponds to the label the relabeling of a particle going around the field. So that is the way to do it. The helicity conservation for magnetic field has been shown in 1958 by Vautier in a PNAS paper, and the statement is simply this: the Lagrangian derivative of helicity should be conserved in time, so it's actually constant. So I'm going to show you this derivation first, and the derivation goes like this. We take the Faraday equation I showed you, and we uncurl it. If we uncurl it, we have just the vector potential associated with B, and then this is the uncurl of the Faraday's equation, and when we uncurl it, of course, we have to introduce a potential, grad phi. Okay, so this is basically the potential version of Faraday's equation. Yes?
The derivative capital D ddt. So ddt just means the physical derivative.
The local time derivative, Euler derivative, not the Lagrangian derivative. Yeah, the physical derivative without the contribution of convective acceleration, of convective transport.
Okay. Give us, especially remind the students about
the difference?
Yes.
Okay, so this is the capital D Lagrangian derivative, and this is Eulerian derivative, local and global. The difference is that local is just a time contribution, okay, nothing else. What is here, other than here? Well, we have the ddt in here, plus the u dot grad of something, in particular u dot grad of A. The convective, the space, convection, in space, the spatial transport of the field. The field can change in time, it can change in space.
So your theory is Newton's. How to extend it to a relativistic form?
Oh, that
I don't think it's a relativistic. How to extend your theory to a relativistic theory?
it can be done. This is the answer.
So it's not a covariant form.
Yeah, you can write it in a covariant form. Absolutely.
But you do not use gamma. I think we use times a gamma in the relativist
Connection.
The connection.
Yeah.
You can rewrite this as with the connection terms. Of course. Yes.
I think the difference is the manifold here.
Oh, this
is
is
flat.
this is flat.
When, according to Wenyu, he is talking about.
I know.
No, this is pi pi t pi pi x, not relativistic. Not the times of gamma q mu, something like that.
This context is Euclidean R3,
Okay.
but it can be extended to higher dimensional manifolds. And of course, you have to take into account curvature and the tensors about that. It can be even, just a note because I cannot talk about that, but it can be even extended with what is called torsion tensors.
Okay, I see.
So non-symmetric Christoffel tensors. Okay, right. So when we have this, what we do, we work on this. We take the dot product with the B here, considering the fact that we have a solenoidal condition. So we'll just, this is just purely algebra. Remember, solenoidal condition for B means that divergence of B equals 0, so that's why we can encapsulate phi B in this. And then we work on this term. And this term, we expand that term, okay, here. This term here can be expanded in this form. So we go back to ddt, A dot B. We take this part on the other side here, and we rewrite all this as a divergent term, okay? So this is what we aim, to have a divergence of something. Once we are there, we plug this term into the integrand of helicity. And so we have an integral in terms of divergence. And this is the game in this field, a classical game after Kelvin, even today, to transform an integral into an integral of a divergent part, and then once we are here, we can use Gauss divergence theorem and use the boundary condition. And so we rewrite the divergence in terms of a flux through the boundary now is a surface integral, and because we took the flux of the magnetic field through the boundary equal to 0, then the whole thing is equal to 0. So that's the way to prove conservation of magnetic helicity. More or less at the same time in France, this was done under magnetic condition. Voltier studied Euler equation. And you see the kinetic helicity is written basically in the same way. We have a field and then the curl of the field projected together. Vorticity, omega, is defined as the curl of the velocity field. And again, we use no flux of vorticity through the boundary of this volume. Okay, how to prove conservation of kinetic helicity? This, as I said, was done independently from Voltier's work. They didn't know one another work. And this was done in 61 in France, and Montpellier. And Moreau passed away not long ago, well, now several years ago, but I had the luck to meet him at the important meeting to celebrate helicity in Montpellier. So I met Moreau in person, and he was a pure mathematician, although he worked on fluid mechanics and helicity, but no application. In any case, we have the Euler context here. We want to prove this quantity, and we do more or less the same, but with different equations. So this is, again, we enter in the integral with the Lagrangian derivative, because remember, vorticity, as magnetic fields, are frozen fields, So this is a frozen field volume. And we can enter in that, and then we apply the derivative to these two fields. We split this, and now we have to use du dt for Euler equations, and then d omega dt, the transport in time of vorticity, from Helmholtz equations. And this is done, of course, du dt, you may remember that is equal to -1 over the density grad P, the pressure. So we substitute this is Euler's equation. This is a little bit more elaborate to write d omega dt in this form, but this is the Helmholtz equation, is work due to Helmholtz 1858. Okay, once we are there, we do the following. We use again divergence-less condition for omega. Remember, omega is the curl of the velocity. So this is always true. It's a kinematic statement. And then we can rewrite this integrand in this form. You see here, a half u squared is called the Bernoulli term, and then minus p over rho from here. And then again, the effort is to, remember the game of that day was to reduce any integral to the integral of a divergent form. And so this is the form, this one. And once we are here, we are almost done, because we apply again the divergence theorem. And so all this reduces to the flux of omega through the boundary. No flux. This is the requirement, so that means conservation of helicity. Okay. Yes? Yes?
So during the proof, Moreau was using Euler's equation. that means there is no viscosity there.
That's right.
If for the case of NS equation, what will happen?
It will happen.
Any conservation?
Conservation is not at all true. It doesn't hold true for dissipative fluids. What you get is that the change in time of helicity, both magnetic and kinetic, will be expressed in terms of dissipative quantities, viscosity or resistivity, and you can show that the derivative has a minus sign, is going down. So helicity is not conserved, and it will be eroded or dissipated by the amount of viscosity you have.
So the helicity will be dissipated.
Yeah.
To where? To the outside of the box.
No. The helicity will dissipate it because the dissipation will affect the definition of the fields, the vorticity. Vorticity dissipates. To where is a perfectly good question. It depends very much on the physical context. One example. For magnetic fields, where it goes? It goes in temperature. In thermodynamics must be taken in the system because this is isentropic. There are no exchange of heat between fluid layers. But with resistive effects, there is an exchange of momentum, if you like, between fluid layers. And so that exchange of momentum, when it's dissipated, well, it's dissipated in terms of heat, for example.
Okay, so this result is still reasonable or practical. I mean, are we in a big trouble if we are when we are talking about a practical problem?
It depends. Now I'm going to show you what works, and the complement is what it doesn't work. I anticipate what it doesn't work. It doesn't work all this when your fields, magnetic and vorticity, are not totally localized or rather highly localized. When they are distributed everywhere, then of course the chances of decrease of change of helicity are higher. When the field is highly localized, the effects of viscosity is there, but is not so terrible. Well, for example, in magnetic fields, in tokamaks, there is a theory put forward by Taylor, and he says that if the fields are very intense, helicity more or less stays the same. And that has been disputed by others, but under certain conditions of mild resistivity, you can prove that helicity is robust. The people use this word, robust invariance. Meaning robust, it doesn't mean exact, and it doesn't mean weak. Robust is dissipate, it changes, but not so much. So that's why it's still important.
So that means we are in trouble, but not so much.
It depends on the intensity of the field. That's why in my talk, for simplicity, I will show you. Yeah.
Can you, it's Helicity in the fluid dynamics. Can we do it quantize to describe the macro world?
So in quantum fluid,
in quantum systems, we are rather safe. We cannot talk about dissipations in a classical sense, but part of the energy when helicity is not conserved, it goes into acoustic production, acoustic waves. Yes.
So, as far as I know, there is a definition of helicity in high energy physics.
Oh, sure.
So what is the difference between this definition and yours? And
Yes.
is there any physical or geographical interpretation of your definition of helicity?
Sure, thanks for the question. It is an interesting question and puzzling many of us, as students in particular. Yes, if you do quantum mechanics and high energy courses, you learn about helicity. It's a totally different thing. It's the projection of the spin along a linear or angular momentum and has no topological meaning. So it's a quantity that is a projected quantity along a direction, and it changes without any particular rule. Here is conserved in time, this quantity. So the problem is that when they came up with the word helicity, they were a little bit unlucky, because I believe the helicity in quantum mechanics, the word was introduced earlier. So it was already present in literature. But the two things are totally different. One, the quantity in quantum mechanics is not conserved. It's a scalar measure of something. That's it. Of course you are, I understand you are, I mean, there is a curiosity. On one hand, you talk about the spin, on the other, you talk about vorticity. So there is a sense that there is a common ground. There is a common ground, but the projected spin contribution is just a scalar quantity. It changes over time.
So basically, both of this definition is based on the scalar product of two vectors. But
okay. You can use this. You can say both are defined in terms of scalar product. That is okay. Yeah, correct. But here, when we talked about the definition, we have U dot omega. So it's a scalar product between two fields. Okay, two fields. And that makes the whole thing completely different. Although the name is close, it's exactly the same. Okay.
So my question: what is symmetry? The symmetry corresponding with the current, the conserved current, the no source here. So what is your symmetry? The symmetry.
It's the same thing, exactly the same.
The
The rotation, the relabeling of a particle rotating about the other one. The particle in this case, is the velocity around vorticity.
Okay, I see. The same symmetry with two different definitions of helicity.
Yes.
The our helicity is the Pauly-Lipinski the conserved current.
Yes.
But your helicity is another helicity, like the vortex rotation, something like that.
Yeah.
Okay.
Okay. When I said fields localized, this is an example. A vortex in water. Vorticity may be everywhere, but what we like to think is vorticity localized in a thin tubes. Of course, it's an idealization. Okay? So this is just the experiment of a production of a vortex trefoil in water. So this is a real experiment done by the group of William Irvine in Chicago. It received great coverage from the press. Of course, Nature and other journals talked about this. So this is, I think, is a Nature Physics paper. Right. We have from there, a few years later, people worked on quantum vortices. So, for example, governed under Gauss-Michailsky equation, and this is the visualization of a turbulent, highly complex tangle in superfluids. And then, of course, as I mentioned, magnetic fields in the sun. Now, we talked about these two fields and the correspondence between these two fields, the vorticity and the magnetic field that generates one kinetic helicity, the other magnetic helicity. These are the equations. This is what we call Helmholtz equation for the transport of vorticity. This is magnetic correspondence due to Faraday. And these are the definitions. So there is an analogy between these, but the analogy is not perfect. It's not perfect because here we have the velocity u that is related to the current. And here A has nothing to do with u. And so it's not really a perfect analogy. However, whatever fields we consider, we can talk about helicity in one context or the other, and we wonder, okay, if it is conserved, does it have any meaning as for kinetic energy has a meaning? And so the meaning was established and rooted in the work of Moffat in 1969, and then further extended in collaboration with him. And if the field, whatever it is, vorticity or magnetic, is confined in tubular structures, then we can rewrite the integral that you just saw, integral of, in terms of this expression. And this expression, I'll tell you a little bit about this expression because it's quite nice. No integration, but the result is in terms of the intensity, like the charges of these tubes, the fluxes, flux of vorticity or flux of magnetic fields, and in terms of these quantities that are topological in character. In particular, this is the Gauss linking number, and this is the self-linking number. I'll be very quick. I'm sorry, but I have to rush here. Gauss linking number is just a measure of the linkage between two different fields, and you can prove that from this analytical expression, you can reduce the calculation to the overcrossing, undercrossing of a link or a knot under projection. If you have an example like this, you can compute the crossings here by doing this little formula. The crossings has a minimum crossing of 4, and the linking number of this is plus 2. So you don't have to do this, you just go to any projection. Why any projection? Because it's topological, it's not geometric. So if you change projection, if you transform this to that, is the same link, I can tell you, topologically the same link. If you compute the plus and the minus here, according to this formula and this convention, you find the same result. You see, the generic projection displays many more crossings, but the topological structure is given by the same number of crossings. If we have a knot, it doesn't make sense to talk about a linking number, linking of what with what. So we have one knot, and can we do the same as Gauss did? Indeed, this is the work of Calugarianu that was extended to higher dimensional context by Pike. And now we look at the knot as if it were made by two lines. And these two lines give you a ribbon, so the axis of the tube, and the second curve. The second curve is, say, you see star, any curve nearby, and you pick these two curves, and you construct the linking number of Gauss. Okay, you do this, you take epsilon as a measure of this ribbon, and then you take the limit as epsilon goes to 0 of this quantity. This is a ribbon, a mathematical ribbon between these two curves. When you take the limit of the Gauss linking number, you get a quantity that is still conserved topologically, and is called self-linking. Self-linking of a knot, not of a link. And this quantity, remarkably, can be written in terms of a sum of geometric quantities. So remember, this is topological, and these are geometric. They exchange one into the other to keep self-linking conserved, fixed. And one quantity is this one, Ryding number, and the other which measure the coils of the ribbon in space, and the other one is the total twist that can be further decomposed in geometric terms, in terms of torsion of the curve, total torsion normalized by 2 pi, and intrinsic twist of the ribbon around the axis. Similarly, as we did for linking number, also for Ride can be written in terms of summation over algebraic crossing signs, so plus and minus. But then we have, because it's not topological, we have to average over all possible directions. And Friedman thought, okay, what about if we take modules here, we count the crossings independently from the sign, just the crossings that we see. And we have a quantity that is neither topological nor geometric, is algebraic, but is kind of interesting. So here is an example. We have a curve in space making 3 coils. We associate in this projection the signs, and the right is -3, and the average crossing is 3. And then, of course, we can change the crossing sign. Instead of undergoing, goes over there, and the right becomes +3. But remember, we can still keep 3 coils with right only 1, as if it were only 1 coil. Why? Because there is a geometric compensation of +1 and -1 that cancel each other. So you can play with these things, etc., etc. A very interesting piece of work came from Peking University very recently. The group of Yue Yang showed that instead of working on classical fluid complexity, we can reduce this complexity by keeping information on the topology and the geometry of the high intensity fields by doing what? By going to the quantum context. And by the quantum context in superfluid, you can go back, analyze this system, and go back to classical context by analyzing the information on the quantized version. And this is a very interesting pursuit, and is actually...
It's too complicated. How to do the comparison? Too complex.
Yes.
So how to do it? To see it is...
I tell you what to do. You take this system, and then you lower, at least numerically, or ideally, you lower the intensity of the vorticity field. You lower, you lower, you lower until you see the most intense vorticity lines. You evolve the most intense vorticity line, numerically, for example, and you compare the evolution with the same distribution of lines, but made of quantum defects. And you can show that the evolution is remarkably similar. This is another open issue. Why is remarkably similar? It's an amazing result of the last 10 years. People wonder if the system is totally different. And the dissipation is totally different. In quantum system is in acoustic and mechanical waves. In physical real system, you have dissipation in terms of entropy, and classical entropy is a mystery. Also the Kolmogorov spectrum of energy decay is not identical, but very, very close. So this is an open question. Why the systems do behave so closely one another. And on the basis of this observation is the proposal of Yale. Yeah. Okay, so the question is to relate energy and to relate energy decay to topological simplification. And so remember, this is kind of initial state, this is a kind of final state, and then I will be also quick here. Why it happens this? Because there are reconnection of field lines. Now we are going into real systems. So no ideal system topology is broken because reconnection of field lines as anticipated by Feynman, 1955. He proposed this idea of reconnection of fields and then evolution of topology. And what happens is this is a close-up view of a real production of vortex filaments in water, where you see the filaments, one here, one other there, are reconnecting, and they are opening and departing from each other. This is just a schematic view of the reconnection process. At a certain point somewhere here, they talk to each other, they shake hands, and they leave apart. And so topology is broken in this fashion. Of course, because of reconnection in real fluids, then the evolution does not concern topology, so you have a production of a trefoil knot, and then this trefoil knot reconnects to form uplink, and then a long evoluted loop, and then even apart two loops. And so this is pictorially what happens, and this has been done by Simone Zucker, basically using Gross-Pitagevsky equation. This is Navier-Stokes equation, if you like, and this is just Gross-Pitagevsky equation. You can reproduce the same thing. Of course, this is under numerical simulation, but you can prove that the evolution is the same. So we have a cascade, what we call a cascade from complex systems, say, in this case, really simple, a trefoil knot, down to unknots. Okay, now, 2030, or 25 years ago, I proposed to do an experiment, and I want to tell you something very quickly about this experiment, and then after 25 years, I'll give you any information about modern work. So the experiment was this. Okay, we have a tangle. Imagine here to go reverse in time. Imagine that you pump energy. Before is just a decay, natural decay. Here is the opposite. You pump energy. Why you want to pump energy? I want to pump energy because I want to get something highly entangled. Highly entangled. And at the time, the way to do this highly entanglement was either to run a simulation to produce turbulence, or to start with something simple and superpose what is called an ABC flow. ABC stands for Arnold, Beltrami, and Childress. The three Childress still alive, as a current institute professor, now retired. Arnold passed away some time ago, I'm afraid, and Beltrami, a mathematician from Milano, of late 19th century. Well, the mechanism is to superimpose, like a turbine, sine and cosines on something simple, so that you get highly entangled system. And then, when it's highly entangled system, you can measure by the complexity that is growing what's going on. Now, this experiment, yes?
I have a question. Is you say this? You say how two topologic have a connect, but this connect is random.
Yeah, sure.
But this shape you say is to be complex.
Yeah.
So that's why. Because I think it have a connect, but this be complex. That's why.
The vortices. Okay. The only steady solution to Euler equation is a vortex ring. All the other possible shapes, they are unstable. They reconnect and they change. They change shape and they reconnect. So this thing, when you see something like this, there is a reconnection, and this is totally random. Oh, totally random. Maybe not, but to the best of our knowledge, we cannot control them.
So you say
reconnection take place. You launch the system, and then the reconnections take place according to laws of nature. We have to understand these laws well, but we do understand locally what happens. but locally. Globally, it's just a lot of reconnections.
All of this is random, but
Yeah.
how we do the research?
Well, you evolve this system and you look what happens. Yeah,
So,
sure.
They were just pumping energy into the
You
system.
pump energy. It's like, I give you an example. You have water. My best example for everybody, myself first, is you have water and you heat up your water to boil things. At a certain point it boils. It changes state, right?
Yeah.
It goes through a transition, phase space, but also physical space. How do you control the bubbling of the boiling water? If you want to create a bubble from heating, one single bubble from heating, yeah, maybe you can understand the details. But if you have a pot that is starting to boil, that is random.
I think it's like a three-body problem.
Yes, in a sense. Yeah. I don't know if you intend it technically. If you intend it technically, yes, it's very close to. Yeah, it's a chaotic system. Yeah. Okay, so this is the idea. The idea is, okay, I go to the expert, Carlo Barenghi, and they say, Carlo, you use your simulation, your software to entangle the system. Once it's entangled, it's in the computer. Remember, we are talking 25 years ago. You have a tangle in your computer. You know everything in the computer. So you project down the tangle and you count the crossing and you put signs and all that. And you can imagine 25 years ago, Carlo, we said that he couldn't understand the thing. Said, this crossing. Said, well, what do we do with these crossings? I said, wait. We have to do step by step the work and see to find out a relation maybe with energy. With energy by crossing counts. That would be great. Very, very economical. Okay, so the idea is, okay, we do all this, you take a projection, and then another projections, and then other projections, not infinitely many, you don't have that time in life, but a few good projections. How to choose the projections is a technical bit, but I'll show you. And okay, we can measure the right from counting on average over all possible projections. We don't have time to do all possible projections. So we have to fix that problem. The linking is easy, it's topological. You take a projection, one projection, and then you count the crossings. You teach the machine to count the crossing, that's it doesn't change in time. Okay, that's easy. And then the average crossing number, I told you, is neither topological nor geometric, is an algebraic measure of complexity. I said, let's focus on that too, because maybe it's interesting. It's in between the two, so it's okay. And then, again, here average, meaning infinitely many projections, we cannot do that. So what about something simple? We take 3 projections, X, Y, and Z, we average the information, and we have a mean information for the exact right, and the mean information for the exact average crossing number. Remember, right, average crossing number, linking number, all these quantities were defined in terms of integral. Not only crossings, but at the beginning, integral. And in the machine, we can teach the machine to integrate over all these curves. These are polygonal curves in a discrete environment, but we can integrate them. So we have also the integral information and the approximated information from estimates of crossings. Okay, this was done. It took some time. This is the result. And there is an initial period of time where the tangle is not mature, is not uniform. So we exclude this part. And then we focus on a place where a time where a tangle is rather complex. And we perform the computation. We have energy here, normalized, and the length of the tangle. They should go more or less the same, indeed they do. This is obvious because energy is localized on a filament and is nothing elsewhere, is a superfluid simulation. And here are the curves. This is scattered, is linking number, and then of course we have these other curves. By the way, I put here the exact analytical calculation of average crossing number compared with the estimated one. And the same can be done for the right, but there are no differences. So that proves an efficient way to work. And then the log of h of the kinetic energy, and the kinetic energy is computed through the integral of u cross omega. All right, so we can compare this, and what is the conclusion of this is if we relate crossings, average crossings, or helicity, and energy, we have this relationship. Now, this relationship is kind of remarkable, has not been tested since then, so we, as scientists, we have to keep our criticism open, because if it were confirmed, in general, it would be a remarkable step, because you can measure energy through a measure of complexity. But I am a little bit careful, and so we wait for further tests on this. However, the direction is to establish a relationship between energy of the system and a form of complexity that you measure. All this was done 25 years ago. So what about now? Because it's time to talk about current work.
So that results comes from your guessing or observed?
No. This is you see it here. It's in a log scale. The power law.
Yeah.
This goes like 82 per second, and this goes 164 per second.
And how to observe E bar? E bar just comes from the usual definition for energy. Different.
Kinetic, in this case, is purely kinetic energy.
Okay.
Yeah. Divide E bar means with normalized with refer to the initial energy. All because these are all pure numbers. So all these have to be pure numbers as well. Now, is energy complexity relation for a freely decaying system, which is what we want. We want to understand if there is something like this. Energy decaying system is any system. And here we are not in ideal case. We are talking real fluids. You saw what happens. You start with a very complex tangle, you let it go, and it decays through reconnection, and then it dissipates and energy disappears, so to speak. It goes into heat, acoustic waves, or whatever, other forms. So, do we have a chance to check on something like this with all these ideas in mind? This is the project. So the project is, okay, what about taking Borromean rings? Borromean rings is simple. Borromean rings meaning, say, vorticity of magnetic field confined in these tubular shapes and with this topology. And let it go, let it evolve. Is simple, but it's not so simple. It becomes a little bit more complicated. So we take the Borromean rings in this shape, and here is Professor Liu's project. So it started more or less a few years back by taking the Borromean rings, just putting the Borromean rings as ellipses into a numerical box and let it evolve. What happens? And so he was lucky to find somebody very patient and to look for the degenerate path. How it goes? It gets very entangled, not entangled at all, localized entangled. So the patient person was or is Hao-Guan, and Hao-Guan provided, after a little bit of work, a diagram of all possible decaying paths. This is remarkable in itself. The drawing in itself, it is a piece of art. So I liked the drawing very much. And imagining the reconnection take place here, maybe here, or all different sides, and according to the reconnection envisaged thought, then you have different ways to go. Now, my time is up. And I started with the question, energy relation, and I can tell you that the energy relation question is still open, but I want to show you some of the results. And some of the results in front of the author, Professor Liu, I will take only 1 minute. It's not my, my point to present others' work, but I'm happy to. So this is the evolution of the Borromean rings in time. If you want to look at the topology, you have to inspect one by one what happens from the numerical simulation. You can identify the initial configuration, and then it goes to what we call Wharton link and the connected sum of uplink, and then it decays to trefoil knot, uplink, and several loops. The work is too complicated and long for me to tell you something in a few minutes, but the various angles of mutual inclination have been checked, and according to the angles, different types of decaying patterns have been found. And this is my final picture of from their work. This is analysis of all the pathways of complexity against the right, etc., and many other things. Of course, this work is not finished because I started telling you something about energy and complexity relation, and this is the piece of work that in collaboration with Shin and Hao we are still pursuing, and we hope to have, we have already some results, preliminary results. We hope to submit the work in the coming months. So this is my closing. 30 years ago, 30 years ago, we published this paper on Physics Today, and they gave us also the cover picture, and the cover picture is taken from simulation of plasma physics, plasma magnetic lines in a spheromac from Japan. And after 30 years, we have a book on knotted fields that we edited with my co-author, Professor Liu. So thank you very much for your attention. Thank you.